Hey guys, Dibyajyoti here from The Fast Engineer, and what I'm about to show you might surprise you. Your fridge, washing machine, even your computer all have electricity inside them. But why don't they shock you when you touch them? One small missing connection and the same appliance can become dangerous. Today you will understand earthing and grounding so clearly that you will never forget it. Most people say it's just a wire going into the ground, but that's incomplete. Electricity doesn't disappear. So, where does it go? And why doesn't it pass through your body? Because of one powerful concept, earthing. Let's define it. Earthing is the process of connecting the non current carrying metal parts of electrical equipment to the earth to prevent electric shock. Simple meaning, earthing is for human safety. Imagine a refrigerator. Inside it, a live wire carries current. If the electrical insulation fails, a small amount of current can start leaking. This is called the leakage current. Now, if this leaking current touches the metal body of the refrigerator, the entire body becomes live. If there is no earthing and you touch the refrigerator, current flows through you. Even a small leakage current can be very dangerous. But if earthing is present, the metal body is connected to the earth using a low resistance wire. And inside the ground, we use metal plates or rods with large surface area. But how do we actually make resistance low? We know this formula. This is the equation for the resistance of a conductor. R equals rho multiplied by L divided by A. Here, R is resistance. That means how much the material opposes the flow of current. Rho is resistivity. It tells us how strongly a material resists electricity. For example, copper has low resistivity, so current flows easily. L is the length of the conductor. Longer wire means more resistance because current has to travel a longer path. And A is the cross-sectional area. Basically, how thick or wide the conductor is. Now, this is the key idea. Resistance is inversely proportional to area. That means if area increases, resistance decreases. So when we increase the surface area, we give current more space to flow, which reduces resistance. And that's exactly why in earthing, we use large metal plates or long rods in the ground. More area, less resistance, easier current flow. Now compare this with a human body. Human body resistance can range from about 1 lakh ohms when dry to around 1000 ohms when wet. While earthing resistance is usually below 5 ohms and in good systems, even less than 1 ohm. So electricity has two choices, difficult path through your body and easy path through earthing wire. According to Ohm's law, the current I equals V divided by R. So lower resistance means higher current. So almost all current flows through the earthing wire. Technically, current flows through all available paths. But because earthing resistance is so low, more than 99% of the current flows through it. And only a negligible amount may pass through your body. But even a small current can be dangerous. That's why proper earthing is extremely important. Good earthing makes the current through your body almost zero. And that's what protects you. Like water, if one path is wide and easy, water flows there. Electricity behaves the same way. If earthing wire breaks, no safe path exists. So when you touch, you become the path. So that is all about earthing. Now let us go into the definition of grounding. Grounding is basically the process of connecting a current carrying part of an electrical system, usually the neutral wire, to the earth to maintain stable voltage and proper operation. In simple terms, grounding is for system and machine safety. In most systems, neutral is connected to earth at one point. This is called neutral grounding. Why? Because electricity needs a reference point. Think about height. If I say a bird is flying at 100 meters, you ask 100 meters from where? From sea level or from the roof? The earth is our electrical sea level. It's the absolute zero. By grounding the neutral wire at the transformer, we lock it to 0 volt. This keeps the entire system stable. Without this connection, voltage can become unstable and equipment may not work properly. So here's the big idea. Earthing is a safety path for faults. Grounding is a reference point for normal operation. Let's look at a home example now. Here's something you see in real life. Now, if you open a plug, you will see these wires have specific colors. In modern standards, like you will find in the UK or Indian homes, brown is live, blue is neutral, green or yellow is your earth. But wait, if you live in an older house, you might see the classic setup. That is red for live, black for neutral, and green for earth. While these colors can vary slightly depending on your country or the age of your building, the purpose of that earth wire never changes. It's always your safety line. This color coding helps electricians identify wires quickly and avoid mistakes. So next time you open a plug or see wiring, you will know exactly which wire does what. Now understand this clearly. Earthing is used for human safety. It's connected to the metal body of electrical equipment. It works only during a fault condition, so it protects you from electric shock. On the other hand, grounding is used for system safety. It's connected to the neutral wire of electrical system. It works continuously during normal operation. So it protects the system and ensures stable operation. So remember, earthing protects people and grounding keeps the system stable. It protects the system. Now look at a 3-pin plug. This is a real fridge plug. It may vary depending on the country, but the concept remains the same. This is the live pin, this is the neutral pin, and this is the earth pin. Now notice something important. The earth pin is thicker and bigger. But why? Because a larger contact area means lower resistance that we already discussed. That gives a stronger and safer connection with the socket. And there's one more important design feature. It's slightly longer than the other pins. So it connects first and disconnects last, which means safety is always maintained. Does current disappear into earth? No, electricity always flows in a complete loop. Earth is not a sink where current gets lost. It acts like a huge conductor with very low potential, approximately 0 volts. So during a fault, current flows into the earth and it eventually returns to the source through the complete circuit path. So next time you see that third pin, don't ignore it. It's not extra, it's your protection. Now that you understand this, you are ready for the real rule of electricity, Ohm's law. The video is right there on your screen. Watch it next, you will never forget it again. For more engineering secrets, consider subscribing. I will see you in the next one.